Welcome back to Unraveling Human Physiology, where we try to make physiology easy for you to understand. Hi, in this video I will show you an animation of the bicarbonate reabsorption of the proximal tubule of the kidneys. But before that, just to understand, why is bicarbonate so important? Bicarbonate is important because it's the most important pH buffer in the blood. Most precisely is the combination of carbon dioxide and bicarbonate which makes the buffer. Look, go to my previous videos where I explain you what is a buffer and what are blood buffers. One of the reasons that carbon dioxide bicarbonate is one hell of a buffering system is that you can regulate it in two ways, separate ways. Carbon dioxide can be regulated in the lungs, while bicarbonate can be regulated in the kidneys. Looking into the kidneys have two roles in bicarbonate regulation. The first one is to reabsorb bicarbonate that is filtered in the glomeruli. And the second one is to synthesize de novo the bicarbonate that is consumed while buffering fixed acids in the body. Today I will explain you how bicarbonate is reabsorbed. Let's start by looking into the bicarbonate problem. Bicarbonate in plasma has a concentration of 24 milliequivalent per liter, and we have about 3.5 liters of plasma. Look, go to my previous video that I explained you how to calculate the plasma volume. Well, if you multiply 24 milliequivalents per liter times 3.5 liters of plasma, you will get 84 milliequivalents of bicarbonate in total circulating in the blood. When plasma reaches the kidneys, with its 24 milliequivalent per liter, it is faced by a globular filtration rate of 190 liters per day. So the bicarbonate load would be the GFR times the concentration of bicarbonate. And that will give us 4,320 milliequivalent per day of bicarbonate that are filtered in the kidney. A disaster, you see the problem. We only have 84 milliequivalent of bicarbonate in blood, but we filter per day 4,320 milliequivalent of bicarbonate in the kidney. So if the kidney is malfunctioning and is not able to reabsorb all of the bicarbonate, it will be very easy to lose some of the 84 milliequivalent of bicarbonate that we have in blood. And if that happens, pH will lower in the blood and then in all of the body, and that will be a huge problem for the body because pH will mess with all the function of the body. Look at my other videos to know why. So to avoid a huge acid-base problem, kidneys need to reabsorb the bicarbonate that was filtered in the glomeruli. And it's very effective doing so because about 99.99% of the bicarbonate that was filtered is reabsorbed every day. That gives us only 0.01% of bicarbonate that is lost every day. That's very little, and that's why bicarbonate filtration by the glomeruli is normally not a huge acid-base problem. And does every part of the nephron reabsorb bicarbonate in the same way? No, there are only certain parts of the nephron that can reabsorb bicarbonate. The most important one is the proximal convolute tubule that reabsorbs about 80% of bicarbonate. Then there's the thick ascending lip of Hende's loop that reabsorbs about 10%. We have the distal convolute tubule that reabsorbs about 6% of the bicarbonate that is filtered. And finally, the collecting tubule that can reabsorb about 4%. So here's the key point about kidney bicarbonate reabsorption. Kidney filters every day more than 4,000 milliequivalent of bicarbonate. In order to avoid a huge acid-base problem, kidney reabsorbs most of this bicarbonate, about 99.99%. Most of this reabsorption occurs in the proximal tubule. And what's the mechanism of bicarbonate reabsorption in the kidney? Let's remember that once blood is filtered in the kidneys, it goes into the nephrons, more precisely into the lumen of the nephrons. Once inside the lumen of the nephrons, if the substance is not reabsorbed, that is, it goes from the lumen to the basolateral space and then enters the blood through the systemic blood capillaries, the substance stays in the lumen and then it will go eventually to urine. But kidneys have the capacity to reabsorb in a controlled way certain substances. To do so, the walls of the nephron are covered with epithelial cells. Epithelial cells are polarized cells. That is, they have a side that faces the lumen, another side that faces the basolateral spaces. Between cells, there are joined by tight junctions that can regulate the flow from the lumen to the basolateral space. If tight junction is very tight, like in collecting duct tubules, water and substances will not be able to traverse the cell unless we have a transporter. If this tight junction is not tight, like in the proximal tubule, substance can go through this space more easily. In order to understand the process of bicarbonate reabsorption, let's remember that carbon dioxide and water react with the aid of carbonic anhydrous to make carbonic acid that can split to form protons and bicarbonate. Let's review step by step what is happening. We are in the first part of the proximal convolute tubule and all the bicarbonate has been filtered and is in the lumen. In the membrane of the epithelial cells, in the external part facing the lumen, we will find the isoform form of the carbonic anhydrous. One of the bicarbonate that is in the lumen will react with a proton that is also in the lumen to form carbon dioxide and water. As both carbon dioxide and water are little molecules and neutral, they can trespass easily the membrane of the epithelial cell. Once inside the cell, they will react again with another carbonic anhydrous. This one is the intracellular carbonic anhydrous 2 to form proton and bicarbonate. Bicarbonate can reach the basolateral side of the cell because it can go through the basolateral membrane because it is a charged molecule. It has a negative charge. So it needs to go through transporters. In this case, the chloride bicarbonate transporter or the sodium bicarbonate transporter. That's it. Bicarbonate is now in the basolateral side, so it has been reabsorbed. Then it can easily reach the capillaries because the membrane of the capillaries is ready permeable to bicarbonate. Once inside the cell, we'll still have protons that need to reach the lumen to start the reaction all over again. But protons are also charged, so they need transporters. In the proximal tubule, mostly the isoform 3 of the sodium proton transporter, but we also find the proton pump ATPase. And here's protons that have reached again the lumen. They are ready again to react with another bicarbonate. So kidney bicarbonate reabsorption is a bit complicated. So let's make it simpler. we have bicarbonate in the lumen that we need to reabsorb. This reabsorption occurs with the aid of protons that come from the cell. Bicarbonate and protons react to form carbon dioxide. Carbon dioxide enters the cell and we have the reverse reaction. That is, carbon dioxide forms again bicarbonate and protons. This bicarbonate can exit the cell, and in this way it will reach the blood, and that's why we can reabsorb bicarbonate. And to be able to reabsorb more bicarbonate, this proton that is still alone goes again to the lumen, and then we can start all over again, reacting protons with bicarbonate to form carbon dioxide that eventually will help reabsorb bicarbonate. So remember this key point: for bicarbonate reabsorption, we have to recycle carbon dioxide with the aid of secreted protons. So let's now look in action all the animation with all the steps occurring all by one, so you will have an idea of how this is occurring all over again. So remember these two key points. Along the nephron, the general mechanism of bicarbonate reabsorption is the same. What changes from segment to segment is which transporter is doing the exit of protons and bicarbonate, and which is the magnitude of the bicarbonate reabsorption. If you like this video, please give me a like, subscribe to my channel, and activate your notification to know when my next video will be on. Thanks, bye!